All right, I think we can start. Welcome everyone to this week Autonomy Talks. This week is a great pleasure to have with us Professor Lerrel Pinto, who is an assistant professor of computer science at NYU. Something about Lerrel, so he received a PhD degree from CMU in 2019, and then he moved to California, where he did a postdoc at UC Berkeley. In general, his research interests focus on machine learning and computer vision for robots, and his work on large-scale robot learning received the Best Student Paper Award at ICRA 2016 and the Best Paper Finalist Award at IROS 2019. Also, several of his works have been featured in popular media. I think there are nice videos representing these works on his webpage, so I invite you to go visit and see these fancy robot videos. And today, Lerrel is going to talk about the surprising effectiveness of representations for robotics. Of course, this is a topic which is very important for the audience of Autonomy Talks, and that's why we are very happy to hear the talk. So without further ado, Lerrel, the stage is yours.
Yeah, thank you again for the wonderful introduction. So hi, everyone. And during this talk, if you have any questions, feel free to interrupt and ask questions. So before we get started, I wanted to show you a video clip. So this is a video clip from the show, which is called The Home Edit. It's a recent show which I've been binging. So what happens on this show is there are these two ladies who go to people's houses and they try to organize their homes, right? So here you can see a scene where, things are in a cluttered environment and these two ladies have to figure out how to clean it all up. So they first look at the scene, they try to understand where everything is, they try to play around with it a little bit, try to see where it could go. During this process, they find things which they were not expecting. So I think they find this like toy snake, which they were totally not expecting. And then after that, they get to work. They arrange, they clean, they're able to put things in the right place and organize this house. So after they do it, they then invite the homeowner back, and the homeowner is shocked at how beautiful their place looks now. So when I first started seeing these videos, it was just so amazing, right? Because it's this thing where a human can just go to any other human's house, and within a few hours of being in that place, it's easy to figure out how to interact with these objects, how to move them around, how to rearrange the scene, and do these things in a very competent way. And so obviously, as a roboticist, the question that comes to mind is, can we actually do this with robots? Can we actually make robots that can go out there in environments that it's never seen before and still be competent enough to work in those environments? Now, the answer to this question right now is no, we don't have robots which can actually do this. So let's try to see why we don't have these robots and what can be done to make our robots go towards this sort of end goal of being able to generalize in the sort of unknown environments. So overall, I think that there are two main key issues for robots to learn in these type of environments. The first issue is observations, that is to deal with high dimensional image observations. So to understand why this is a problem, let's take an example of a self-driving car, which is equipped with a camera in front. And so the observations that a camera of this sort would see is something of this sort, right? So an image of the scene with a bunch of cars, a bunch of pedestrians, all in the scene. Now, this image-based observation is quite high dimensional, right? So this image itself has maybe 2 million of dimensions in it. And so trying to reason about the scene from this high dimensional observation is quite hard because there's so much of information in the scene. But when we see the scene, we know that the true information in here is not in the space of millions of dimensions. In fact, when we see the scene, we sort of reason about the scene in terms of, oh, there's a car, there's a human, where they are, etc. And so the true state of the scene is often quite low dimension, maybe a few hundred dimensions over here. So the obvious question is, okay, why don't we just infer that state and try to then reason about the scene from that state, right? And this is exactly what a lot of roboticists have been trying to do. But what we have found is that estimating state in the real world is quite hard. So if you're a self-driving car, you need to put a suite of sensors all over the car, radar, LiDAR, a bunch of cameras. And then if you're doing it inside homes, again, you need to put this rig of cameras all around the scene if you want to accurately estimate the scene, the state of everything inside that scene. Now, in a lot of cases, even the sort of notion of state becomes ill-defined, or maybe it's even higher dimensional. For example, if I show you an image of a cloth, for instance, what is the state of the cloth? Or a rope, what's the state of the rope? How do you describe what the rope shape is with very few dimensions? It becomes a hard problem because it's a sort of it's not a rigid object. Right? You have a similar issue if I show you an image of a tree. What is the state of the tree? Will you model every single leaf on the tree? Or if I show you like a dirty table, would you have to model every single speck of dust to get this true state of this table? So this is our first issue. How do we make robots that can sort of reason about the world from these high dimensional image-based observations? The second challenge we have is reasoning over long horizons. So again, let's look at our self-driving vehicle example over here. So if I ask this agent a question like, what is in this image? This question is easy to answer, right? I just take this image, I go on to clarifai.com and see what the outputs are. So it'll immediately say that there's an adult in the scene, there's a person, car, street, road, transportation system with very high accuracy, right? And so we already have machine learning tools for this problem. And the reason for that is because this problem is very easily cast into a supervised learning problem, right? But if I ask a slightly different question, let's say I ask a question of, where should I go? Which probably is the most pertinent question for this car. Answering this question is actually a lot harder than the first one. And the reason is that the effect of the output here, it lasts over time. So for instance, if the car says, I want to go left, it may crash into oncoming traffic in the future time steps. If it says go straight, it may crash into the person in a future time step. So it should probably go right, because if it goes right, it's probably not going to crash into oncoming traffic and not going to crash into the person. So this sort of flavor of problem where when you make a decision, the sort of decision you make, it affects what you see next. And that keeps happening step after step for a long amount of time, makes this problem hard. So how do we solve this problem? Well, one way of solving this problem is to recast the problem into a one-step sequence. So you try to look at your problem and see, okay, how can I reduce this sort of sequential aspect and just try to model one single step of information. And we have sort of focused on this in past work where we're able to use this idea for a bunch of problems like how to grasp objects, how to fly a drone without crashing into scenes, and also trying to implement things on real world small robots, as you can see on the right here. But the issue with this sort of recasting of the problem into a one-step sequence is that it's not a general solution. You have to do this for every single robotics problem that you would face. And a general robotics problem is not easy to recast into this one-step sequence. So this is our second issue, reasoning over long horizons. So just to summarize the two key challenges and sort of trying to reflect that into what do we want from our robot, there are these two things, right? So the first one is we want our robots to be compatible with these high dimensional visual observations. And the second is that we want our robot to be competent in situations where it has to do a sequential decision making. So how do we go about creating a robot that has these two properties? So before we go into this, let's actually look at what's happening in other fields of AI. So this is a quick detour. So let's try to see what's happening in, let's say, natural language understanding. What is the most exciting research happening in this field? Now, undoubtedly, one of the most exciting things is the use of large language models. So here you have large models that can fit large amounts of unlabeled data. And once it fits that data, you can use these models to quickly solve tasks, right? And so again, there's a bunch of work in this area. If you're interested, you can have a look at these two references, but there are many, many more works on this line. How about in computer vision? What's happening there? Now, again, one of the most exciting ideas here is to take large models, fit it with large amounts of unlabeled data. And once it's trained with this large amounts of unlabeled data, you then use it to solve a downstream task with small amounts of labeled data. And again, if you're interested in this, I've linked two papers here, and even apart from these two papers, there's a rich amount of literature over here just in the last 3-4 years. So in general, all of these works, they follow the same central principle. And that's the principle of self-supervised representation learning. So what does this mean? What does self-supervised representation learning mean? So first, let's look at just the last two words. Let's just look at representation learning. So here, what this means is you have some sort of an input. This input is normally high dimensional, something like an image or a long sequence of text or a video or sound information, something which is high dimensional. Then you take this high dimensional information, you feed it into a neural network, which is in this case called an encoder. The reason it's called an encoder is because it encodes this high dimensional information in something which is lower dimensional. And that lower dimensional thing, which I'm going to call ZT, is called a representation. It's a representation of that high dimensional input. So when we say self-supervised, what self-supervised means is that this encoder, this thing which sort of creates these low dimensional encodings, is trained without labels. It's trained without explicit labels of what the representation needs to be, right? So you may have a question now that, okay, how do we actually train this without any labels? So again, there's a rich amount of work over here, but just to give an intuitive idea, if you have some amount of spatio-temporal data, what you can do is you can mask one slice of the data, pretend that that slice, it doesn't exist, and try to predict that slice given the other slice. So an example for it is, let's say you have like a sequence of information here. Given the information of the past, you can try to predict what happens in the future. Or given the information of the recent past, you can try to predict what happens in the future. Or given the information of recent past, you can try to predict what happens earlier in the past. Or even if you don't want to operate in terms of a temporal data, even for spatial data, you can take a slice of the spatial data and try to predict one slice given the other slice. So again, there's a rich amount of literature here, but the key idea is that you just use that input data. You're not having any extra labels, right? So you have this input data and you formulate a learning problem from that input data. Okay, then what's the point of this? What's the point of learning all these self-supervised representations? The point is, once you learn this, if you now have a downstream task, let's say image classification or detection, or doing a question answering problem, or doing a text completion problem, I can use this encoder with few amount of labeled data and quickly solve these tasks. Right. Now, this sort of formulation of doing first we do self-supervision to train an encoder, and then we do a downstream learning for the task is sort of the state of the art in natural language processing and computer vision. That's the way in which you would first start to solve any of these type of problems. Okay, so if this is the most prominent way in these two fields, how about in robotics? How do we use this idea in robotics? So the most straightforward way is as follows, right? You take the robot information. So in this case, robot observational data, high dimensional images. We use this high dimensional data as our input. We train an encoder. So the encoder takes this high dimensional observational data, encodes it into something low dimensional. And then once we train this through self-supervision without any labels, once these features are trained, we can then use this to optimize behavior. We can use this to figure out what actions need to be taken, for instance. Now, to do behavior optimization, you can use your favorite toolbox. You can use imitation learning, you can do reinforcement learning, you can do model predictive control. You can sort of integrate this with a lot of standard tools that a roboticist has. All right. So if we just go back to the desirable properties for a robot, so the first one was being able to sort of use high dimensional observations, and the second one was to be competent when you have to make a sequence of these decisions. What we see is that when you have this sort of self-supervised framework, the encoder allows you to be compatible with these high dimensional observations, because it takes these high dimensional observations and it encodes it into something low dimensional. And reasoning about that low dimensional thing is a lot easier than the high dimensional thing. And then for the second part, if you can create behavior optimization methods that can take in these low dimensional features or representations, you should be able to sort of create competent behavior. All right, so hopefully this gives you an overview of what this sort of self-supervised framework looks like in a robotics setting. And now what I want to do is to go over a few of our works that sort of follows this, this sort of a recipe. So when we start out, we will start out trying to look at representations for imitation learning. So we start off with imitation learning because, at least from what we have seen in our work, that imitation learning is probably one of the fastest ways to learn how to solve tasks. It's also easy to collect data for this. And so that's why we'll start with imitation learning. At the end of the talk, I'll also sort of quickly show you a few works which look at how you can use a representation learning along with other sorts of optimizers like RL or MPC, for instance. Okay, so let's start out with imitation learning. So the first question is, how do you get the data, right? Because before you do any of this learning, you need to have some amount of data. So to get our data, what we do is we use assistive tools. So the way this works is we have a reacher grabber. This reacher grabber has these two fingers at the end with which it can interact with objects in the scene. Then we retrofit this tool with a camera. So we 3D print a mount and mount the camera on the stick. And what this camera gives us, it gives us observations of how this tool is interacting with things in its environment. Then we take the same tool and we mount the same tool on our robot. So now our robot also has a reacher grabber as its end effector, and also has a camera to give it observations. So what you should sort of intuit from this is that the demonstrations that a human collects on the left using the tool, it looks the same from the perspective of the robot on the right, because the action space is the same, the end effector is the same, and the observation space is also the same. So what it means is that you can now take this tool, you can solve a lot of versatile problems in different environments. But more importantly, you can, since this tool is very easy to use, there's no wires coming out of it, you can actually collect data in a wide variety of environments. You can use this tool at your home, your friend's home, outside on the road, anywhere. You can use it to get a lot of this rich visual data, not just in your lab anymore. If you want to learn more about how to use this tool and how to 3D print mounts, etc., feel free to have a look at the paper linked at the bottom. Okay, so now let's see how we can actually use this tool to learn to solve a task, right? So the task we'll start out from is the door opening task. So here, let's say there's a cabinet door, and on the left, there's one of my students, Joe, who is collecting a demonstration for opening a door, right? Now, what we want is, given a few of these demonstrations, we want a robot to also be able to solve this, right? And what it would look like is something like this, right? So we have a robot which can, again, go to the door and open the door, similar to how that human demonstrator had shown it. One of the important things here is that the observation of the scene is only obtained from visual information. It's only from this camera over here, right? So it does have to use this high dimensional observation as input. Okay, so how do we go about doing this? So let's start with how some prior work tries to solve this problem. So one of the most prominent works over here is behavior cloning. And how behavior cloning works is, you have a model. You can think of it as a neural network, CNN. You have some observation into the model. So this is an image. So this is an image of the tool which is interacting with the door. It goes into the model and it outputs an action. The action in our case is end effector velocities. Now, because you already have labeled data here, because you have the demonstration, you can train this model using supervised learning, right? So you feed in an observation, you see the action, and you make that action match the action you saw in the demonstration. Now, the issue with this is that you have to train this whole neural network, this whole model over here, end to end, to output these actions. And training this in an end-to-end manner means that you need significant amount of demonstrations to solve each and every task. So often you need around 500 to 1,000 of these demonstrations. So instead, what we do is, instead of training it end-to-end, we only train a model to learn a representation. So given the observation, we are only going to learn a representation. And then once we have the representation, which is trained through self-supervision, we're going to use this representation in nearest neighbor matching. So we're going to predict actions given only nearest neighbor matching from this representation. So how does this work? So this is our model over here. I'll split this up into training and execution. In training time, we are only doing self-supervision, right? So we use standard self-supervision methods in computer vision. The method we use is called PYOL. The way it works is, given some observation, it makes two augmentations of that observation, and it forces the encoder of those two augmented views to be the same, right? So this is a standard method. If you want to learn more about it, please have a look at the PYOL work. Now, once we train this encoder, in execution time, what we do is, given an observation at a certain time, we first feed it into the encoder and we get a representation. Once we have the representation, we match that representation with the representations of everything seen in the demonstration set. So let's say we have K number of matches over here. Then we aggregate the actions from each of the matches proportional to how close the representations were, right? So in a way, it's like a locally weighted optimization happening over here. So after aggregating all of these actions, we have the sort of aggregated action, and that is the action that is applied on the robot. Okay, so let's see this in action. Okay, so this method is called visual imitation through nearest neighbors, or win for short. And now we can go to what happens in execution time. Okay, so here's our robot. Let's say this is at some step T. It sees an observation over here, right? So this is the image observation. It finds the nearest neighbor matches in the demonstration. So as you can see, they're not exactly the same as this, right? Because like lots of things in the scene has changed, especially on top. So you find these nearest neighbor matches. There are actions associated with each of them. You aggregate these actions using the locally weighted regression method. Then you apply this action on the robot. The robot moves forward. It sees a new observation. And then it keeps repeating this process until it solves the task. So let's see this on in sequence now over here. So here in the bottom right, you can see the observations from the camera mounted on it, and the arrow indicates the end effector velocity that it is supposed to take. So what we're also able to do is, since we can feed any sort of demonstrations now, we can also collect demonstrations for any cabinet door and learn a single model to solve either of these tasks, right? So for both the case on the right and on the left over here, even though the door is opening in a different way, even though the sort of mechanism of the doors are slightly different, the same model is used in both of these cases. So in all of our experiments over here, we only use around 50 demonstrations. So it's quite, it's not really cumbersome to actually collect demonstrations for these tasks. So because we have so few of these demonstrations, what we see is that doing end-to-end behavior cloning, it does not work. It's just too few amount of data to train this whole network end-to-end. But if you use self-supervised features and then do behavior cloning, you get substantially higher performance. But hands down, the thing that works the best is if you do this self-supervised learning and then use nearest neighbors, that works much better than all of the other baselines that we experimented with. Okay, so after this, we then wanted to investigate how robust is this? How far can we actually push this model? So for this, what we do is we have a same scene, but now we try to put a visual distractor in the scene. So in this case, we put this purple tape to sort of cover up all the visually prominent features in the scene. And what we see is that if you put small amounts of tape, it's still able to solve the task fairly often. But then if you keep adding more and more distractors, if you keep trying to remove more and more of the scene, it gets harder. But in this case, it's still able to solve it. But then at some point, if you remove all the visual features that were seen in the initial demonstration, it then entirely fails, right? So the success of this method, even though it's able to generalize to some extent, if you completely change the scene and remove all the features, it's not able to work as well. But if you compare our method with an end-to-end work, what we see is that when you create modifications, our work is still more robust than if you do end-to-end learning. Okay, so if you're interested in this, we also have all of our code and data online. So you can go onto this link and sort of use our algorithm. So at this point, if there are any questions, I'll be happy to take them before moving to the next part. Okay, no questions, so I'll move on to the next part. All right, so I talked about how to open doors using this feature grabber tool, but now let's try a slightly harder task. So let's try the task of doing dexterous manipulation. So over here, let's say you have a robot hand. So this is the Allegro hand from Warnick. And we want this hand to do some sort of in-hand manipulation of objects. Now, the first question again is, how do you get data, right? How do you collect demonstrations for this hand? So the most standard way is to use a cyber glove, but a cyber glove is quite expensive and it requires calibration, right? We also are not able to use our reacher grabber tool because that tool has only 2 fingers, whereas this has 4 fingers, right? And also much higher dimensions, higher action dimensions for each finger as well. Now, another way is if you create a rig. So this is work from NVIDIA, where you can create a rig of cameras. And from this rig of cameras, you can sense a human hand. And from sensing that, you can use a human hand to teleoperate this sort of hand, this sort of robotic hand. So although this becomes a lot cheaper, it means that you still require to calibrate all these multiple cameras with respect to each other, which is again time consuming. But what if we just use a single camera? What if we just take the RGB information from a single camera and try to train a robot from this, right? So this would allow you to get cheap data and also with minimal amount of calibration because you just have a single camera. Now, there's also been some concurrent work which is trying to do this, and I've linked a few works over here which also try to teleoperate a robot just using a single observation from a human hand. Okay, so this is what it looks like in our framework. So as the human hand moves, we use a pose detector to then figure out the pose of the human hand. And once we figure out the pose of the human hand, we can then retarget that pose onto the robot hand, as you can see on the right over here. Now, as the human is moving his hand, they can also see the robot on a screen, right? So they are sort of like doing like some sort of a joystick-like control, but the joystick is their whole hand. Right? So at some point, it doesn't even feel like they're trying to solve an actual task because they're just using it as a mode to move the robot hand. Now over here, this is an example where I put a cube now in the hand, and I'm asking the human demonstrator to rotate this cube inside the hand. And again, as you can see, they're able to do this quite easily after around 5 to 10 minutes of being trained on the system. All right, so now let's say we want to solve the task of cube rotation. We want to train this hand to learn a policy to rotate this type of cube. So what we do is we ask the human to collect a bunch of demonstrations. In total, we collect around 30 of these demonstrations. So all the videos you're seeing here are all the demonstrations that are used for training our cube rotation policy on this robot hand. Now, once we have all of these demonstrations, how do we learn a policy? Right? So to learn a policy, what we'll do is we will just go back to our win algorithm, our nearest neighbor-based controller, and just do the same thing on this hand. And if you do this with some small amount of modifications, we're able to train a policy now, which you can see here, that can rotate a cube. So I think in this example, it was able to do, I think, around 12 360-degree turns without having to stop. So one of the reasons why we have AR tags around is because we also experiment with just doing state-based nearest neighbors. Now, of course, doing state-based nearest neighbors works a little bit better than doing image-based nearest neighbors. So we experiment on 3 tasks in total. So we have the flipping task where the hand has to flip an object without the object slipping off. We have a spinning task where it's sort of a faucet opening task. And on the right, we have the cube rotation task. So what we see is that if you do state-based nearest neighbors, it does fairly well on all the tasks. The sort of worst task for it is the spinning task. And one of the reasons for this is because there's a lot of friction on the faucet. And so it really needs to apply enough amount of force to sort of spin the faucet. What we see is because we only have 30 demonstrations for each task, it's very hard for a behavior cloning model to train end-to-end to solve any of these tasks. So it just completely fails on all of these tasks. Now, if you do image-based, on some tasks like flipping and on cube rotation, we're able to get fairly high amount of success rate. But on spinning, we're not able to get, we're not able to solve this task at all. It was an interesting sort of like detective work to try to figure out why it's not working here. So what you'll notice is this view. This is the same view that our model sees. And what happens is when the fingers move, it occludes the object. And so when it occludes the object, it's very hard for this model to reason about the scene. So hopefully in future work, we may add like a depth camera input or maybe another camera so that it can deal with the sort of occlusion that's happening here. All right. So if you're interested in this framework, if you're interested in teleoperating the robot and also training policies for a robot hand, again, all of our code and data is online, so feel free to use it. So before I end the talk, I want to still, as I've promised, I want to show how we can use learned representations with other sorts of optimizers like RL or MPC. So first, for RL, what we have recently been able to show is that you can combine augmentation-based algorithms along with standard off-policy RL algorithms such that they obtain state-of-the-art results. So here, this is experiments on the DeepMind control suite, where the observations that the RL policy is seeing is the same observations that you are seeing. So for example, on the humanoid example over here, it's able to find a policy to make this humanoid walk just given this image that you're seeing. So just from a single stream of these images. Again, all of this code is online. So if you want to use this image-based controller, you can optimize it using this code. Now, how about for planning? So again, over here, what you can do is you can learn self-supervised models that can predict the future. And if you can predict the future, it gives you a very special ability. So now if I have a start state, let's say I have a start state of a rope, and I have to make the robot move this rope from a start state to a goal state, I can now plan using my self-supervised model, right? So solely from visual observations, it can plan in that space and figure out the sequence of actions to go from an initial, like randomly specified state of the rope to a goal specified state of the rope. Now, the really cool thing about doing this sort of planning is that you can use the same model again. You can change the start state because you can have arbitrary start states, and you can change the goal state because again, you can have an arbitrary goal state. And now again, you can plan from going from that start state to the goal state using our model. So we can also train these self-supervised future prediction models for cloth as well. So here is a few examples of cloth where we first start out with a scrunched up cloth. So we take the square cloth, we scrunch it up, we throw it on the table, and then we ask it to go from that scrunched up cloth to a flattened out cloth. And again, after a few interactions, it's able to open up the cloth and then spread it out. So if you want to see more videos for it and sort of learn more about this method, feel free to have a look at the paper at the bottom of the screen. So with this, I will end for today. And if there are any questions, I will be happy to take them.
Thank you, Lerrel, for the nice talk. If you have any question, you can raise your hand or write in the chat. Let's see. Carlo, do you have a question?
Yes,
yeah,
I
go
have.
ahead.
Hi, thanks for the great talk. I have a question, like, what kind of training data do you use for training your representation? So for the self-supervised part, like, how do you explore the environment?
Yeah, this is actually a great question, and a question a lot of us have also been spending a lot of time thinking about. So right now, in all of these works for the self-supervised part, we are just using the raw image frames in the demonstration. So when you collect the demonstration, we take all of the visual frames, and then we sort of, we're not using any of the temporal aspects. We're just taking the raw image frames, doing self-supervision on those raw image frames. But I'm sure there's probably scope for doing a lot more interesting ways of training this representation itself.
It's the same data that so from the data is coming from the demonstrations, also for the self-supervision. Okay, I see. Thank you.
Exactly, yeah. So you could also train it from sort of unlabeled data. So I can just, maybe take the stick, move it around the scene, and train it from that data. Because in the self-supervision part, the action information is not used at all. It's only the observation data that's being used.
Okay, thank you.
Yeah, thanks for the question.
Any other question? Alessandro? Seems so. We cannot hear you though. So I think Alessandro has a question. He's muted. You can also write it on the chat if you have problems with the mic. I can maybe ask one question in the meantime. So maybe it's a stupid question. I'm not from the specific field, but I really like the storytelling part of the first part of where you explained your algorithm. And then I liked when you explained that when removing, some of the features or the important features from the images, you actually are not that precise anymore. But there I'm not, and there you said, but we can still do better than the state of the art. But I was kind of wondering, what are the next steps there to improve?
Yeah, it's a great question. Yeah, so I think one of the key limitations right now is that the way we are doing imitation learning is that we are only training from offline demonstrations, right? So we have a bunch of offline collected demonstrations. We're sort of fitting a model on those demonstrations and executing it. So if you see something which is very far away from those initial demonstrations, it cannot do anything because there's no correspondence, right? And so I think the way to solve it is that we need to use more interactive data, right? So you have to maybe do some amount of inverse reinforcement learning, maybe just doing standard RL, it could also help, or doing planning, it could also help. So I think what we have right now is we have methods to use representation learning in imitation, in RL, in planning. But I think if we can start to combine them, we can maybe try to solve these sort of problems more effectively.
Okay, thank you. And in the meanwhile, Alessandro wrote in the chat, every time you add some structures to the representations, you learn, for instance, state-based KNN for action matching, then you need less data for successfully training a policy. Do you think that this will trade off a bit of the generality? Or, and if yes, do you have a sense of how much?
Yeah, this is again a great question. So I think there's this interesting thing where we are getting our generality from our representations, right? So from how we learn the representations rather than from the action prediction part, right? And so what we see is that our models are actually more general than these behavior cloning models, is because over there the actions are like clearly overfit, right? But if you do this nearest neighbor based thing, you can only choose actions from the set of actions previously seen, right? You can only choose actions which is in sort of the like a sort of convex combination of existing actions. Whereas if you do a neural network, it can output arbitrary actions when it sees an image which is never seen before, right? So there is a trade-off, but I think also there's a question about in what part of the architecture are you using this trade-off? Because we are actually training with a lot more data in that self-supervision part, because we don't have label data, so we can create lots of like augmentations and things of that sort. So we are training with a lot of data for that initial self-supervision part. It's just that for the action part, there we don't need to use as much data. So it's a great question. Yeah, I think it's a very important one for the coming years. Yeah.
Nice, thank you. And also Alessandro says, thank you very much. So, I guess it's satisfied with the answer. Any final question for Lerrel? If not, I think you can, if you come up with questions by looking at the recording of this talk, I think you can reach out to Lerrel via his webpage, his email. Thank you again very much, Lerrel, for a great talk. Wish you good luck for the next steps.
Thank you for having me.
And thank you all for participating, and see you all to the next Autonomy Talk. Well, by the way, next week we won't have an Autonomy Talk because most of us will be gone for ICRA. So we see us in 2 weeks. Bye-bye.
Bye, everyone.